A very good morning to you, everyone, and very pleased to be here. I think it's more or less 5 or 6 years ago since I was here last time. So I will be talking about TDAB planning and some models and also some the approach to planning in general. I hope you will find it useful. I'm not sure if I will be able to answer the question which prediction model to use. We'll see. Maybe it's something we can discuss afterwards. Okay, so this is the outline here, very simplistic. Requirements, something about guidelines, and planning software. The focus is on number 4 here, which is the prediction models, and then finally some kind of summary. Okay, and first let us ask the question, maybe this is an unnecessary question for most people, but why should you plan? And I think there are several advantages, and I try to list some of them here on the screen. You can analyze the usability of your network, your existing infrastructure, the spectrum availability, and so on. So this provides a sort of a checkpoint to what is possible with your network. So I think this is, and in the end, of course, you would wish to know the cost of what you're going to achieve, what you're going to do. So this is quite important. And in doing the planning, I think the first thing, I've done planning in quite a few countries, and one of the most thing that struck me is that the requirements are, from the very start, very unclear in most cases. So, and I think that is if you know the target, you have a good chance of achieving the target. But if you don't know it, you can wander around in circles for a long time. And in a successful planning, it involves many parties, the network operators, the broadcasters, and also the administrations. That's my view, at least. Okay, and planning is an iterative process. You refine your requirements step by step, and then finally you get to something which you think is this is what I want, and this is possible. So I've listed a few steps here to iterate the plan. First, you have some kind of nominal plan just to get a grasp of what spectrum is available and what the infrastructure is available. And in the end, of course, you do a detailed plan. And in this detailed plan, this is where you design your sites, the antennas. And so what we're going to talk about mainly here after this is the detailed planning when you look at how can I achieve coverage. And the detailed plan is mainly, well, in all cases, almost done by a network provider or a broadcaster. Okay, and talking about guidelines, I think we have I'd like to give some advertisement to this excellent planning guideline from EBU. It's 3391. It's a must read for everyone interested in DAB. It includes a lot of information about TDAB, which is very, very useful. I also found that during the work we've done earlier that it's very useful to have a national guideline. And that means you take some of the information from this 3391 and then add your own personal, your country guidelines to this, your requirements. And that you can, for example, define which procedures you use in the planning, which field strength prediction models, which will be the focus of the presentation, software tools to use, and how you design your SFNs, your single frequency networks. So these are quite, seems very basic, but it's very important because I've been in organizations where they actually did, well, you had several planners and they have done everything very different. So you can't compare the results from the different planners. And a planning guideline is a living document. Be prepared to update it. That's my advice. Okay, let's look at the planning software. This is, of course, our planning software, but there are other planning software. And there are, of course, a lot of prediction models included in it. But what I'd like to stress is that it's very useful to have something which is DAB specific, which allows you to design SFNs in a proper way, which allows you to optimize the network. So this is where you have your TDAB model included. And this is very helpful in the end, in the planning. Okay, let's, for a successful planning, you need a couple of databases. I've listed 3, which are, while the 2 first one, elevation data and clutter data are, I would say, more or less, at least elevation data is mandatory here. Normally a resolution of 50 by 50 meter for elevation data. Elevation data, for those who are not aware of it, is the terrain information. Clutter data is also very, very important, especially since TDAB receivers will be traveling at low height or moving at low height, let's say 1.5 meters. So the clutter information is very, very important here. Population data is used to verify that you achieved a certain planning target. It's not used often in the actual prediction of field strength. Okay, this is an example of a clutter map from Bangkok, and you see the different clutter classes here. I'll talk more about clutter later on. Okay, road data, road coverage. This is a place where you can overlay your existing predictions on the road network, and you can see where are there holes, and then you can decide whether you want to improve coverage, to add transmitters or modify the antenna patterns or whatever to achieve a better coverage. And usually the roads are structured in different layers, like highways, national roads, and more regional roads, and so on. So this is, I think this is a useful tool, as many of the TDAB receivers will be in cars. Okay, now let's look at a few prediction models here. I will not go through this table. It's just for adding some information here. So if you look at the far left, okay. Yeah, if you look at the far left, you have a 3-dimensional model which can be used. And as you move further to the right, you have a more simple model, even a free space model. Free space I wouldn't even call a prediction model, but it provides some information still if you have that. So the ones in gray here, which are marked in gray, I will say a few words about, but it will not be a comprehensive training course on propagation models here, I'm afraid. Okay, so let's talk about, there are 2 main ITU models. We have the 1546, which I guess many of you know already. 1546 is an area general model, and it's based on field strength curves, where you enter your distance and your effective antenna height, and then you read the field strength value, scale it with the power. It's mainly used for coordination purposes, I would say, but I find it has, for planning, it has maybe a little bit of bad reputation in some cases. But it is useful to compare different scenarios. And by adding a feature called clearance angle, where you look at from the reception point to the nearest terrain obstacles, you can make it quite good, actually. Then we have the 1812, which is another commonly used ITU model. And that is terrain-based. It's usually clutter, and then you can use elevation data. So we will look at those a little bit in the coming slides here. Okay, so I have an example again from Thailand here. We have a transmitter in Chiang Mai here, and it's on the side of a hill. And these are the clutter classes. You see the city here in pale red, and these are the legends I used. I think we can discuss these levels later on, but this is one example. And we do predictions at 1.5 meter with 50 by 50 meter elevation and clutter data. Okay, so let's add 1546. No correction, just straight curves. You add effective antenna height. And this is what you get. You see the hill, you see the impact of the hill very clearly, but you also see that it seems to be, it gives some kind of coverage contour, which is not bad. And then if you add the clearance angle, then you start to see the impact of the terrain very clearly. And already here, this is quite a useful picture if you don't have anything else. Now, adding 1812 here, it looks much, much larger, and I'll explain later why this is the case. And no clutter data used. But if we add clutter data, you can see how it shrinks a little bit. Maybe the legend is not properly adjusted, but it shrinks a little bit, which is natural because you are at 1.5 meter, and this is what's going to happen. Okay, and then we have the model we usually recommend, which is a Canadian model called CRC Predict. And that proves, turns out this way. I would say if you look at the area which is covered, if you consider that 48 is enough, essentially it gives more or less the same, you get the same picture here. And so what we did actually, I will not talk about the measurement comparison which we had done, but we adjusted the model. So in real world, the CRC Predict should be quite close to reality, actually, at least the measurements we made in this area. Okay, and let's look at the two different profiles here. One from the transmitter across the flat terrain, and you see the transmitter on the left-hand side at the height there, and then you have the receiver on the other side. So if we now add the different models here, let's add CRC Predict along this path. It's a straight line out across a flat field and at the end some hills. So this is the result. And then if you add 1546, since it's a flat area, you don't get very much effect of the clearance angle here. And then we have the free space. So somewhere between these, we should expect some kind of result. And if we add now 1812, we see that it gives substantially higher levels. I'll try to explain that in a few seconds here. Let's have another example. And if you go up the hill, which, I mean, this is quite extreme. It's a lot of hills. But if we do the same thing here, adding CRC Predict, you see how it's going up and down very much. And if we use 1546 now with clearance angle, it follows the same, you see the same kind of correlation here. It correlates very well to each other. And also adding, well, free space, you see that some points are clearly points where there is free space, and the propagation model has probably identified this. And if we add now 1812, you see it fits very well with CRC Predict. So depending on the environment, you can get different models could be usable in a sense. Okay, yeah, and I would like to explain the different, I mean, in the flat field, in the first set of I showed, then the 1812 is traveling across a flat field, and you only have the clutter. So the clutter is very important. And in the model I used, I would need to adjust the height of the clutter to make it work better, to make it work in the way I wish to use it. And this is what we've done with the earlier CRC Predict, which I talked about. So actually, if you adjust the height, and then you also often set a distance from the obstacle, the wave comes in here. And if you have those two parameters, you can quite easily adopt the 1812 to fit more or less, give more or less the same result. as you had earlier. Okay, yeah, I will drop this slide here. Okay, there's something about, let's leave a little bit the prediction models, the actual models. Here is a difference between 1% of time and 50% of time. And you see that 50% of time you get roughly 60 kilometers from a transmitter in Stockholm. And the other one is for if you use 1% of time, which is 3 days a year, then you will have a much, much larger coverage area. And these models can be based on change of Earth curvature and so on. Or it can also be measurement based. But you need this kind of properties of a prediction model when you design SFNs. So let me show you again, Thailand here. This is a national SFN, 50% of time. And if you look at the red areas, this is where you might expect some self-interference half of the time. And that is something perhaps that you can possibly adjust by timing and antenna diagrams. But if you do it for 1% of time, this is the result. And this is, you wouldn't even try to modify it or may improve it. So that is important. And if we go to the next, try to summarize this, some of the model requirements, I think that you need, the model you are going to use need to be able to calculate at 1.5 meters, which is, I mean, that's basic. And you need, as I explained earlier, the percentage time, which is important. And that's also included in 1812 and most of the models actually, also in 1546. And then in my view, it should have a property, should accept clutter, which is very important considering the low height of the TDAB receivers. And of course, I think the coming speakers will talk about how to adjust prediction models. And I think it's a key issue to be able to adjust it if you are able to do proper measurements. It should also work well with different database resolutions. We used, for VHF, we normally don't go below 20 meters, but that, I mean, that can be discussed, of course. You also need, which is not the prediction model, something that it describes the TDAB properties, which I find very, very useful. Often, the prediction model could be a kind of national standard or decided by a property that you should use this to present a certain coverage to your to the administration to prove that you met your coverage target, but that doesn't stop the network provider to make a good job and try to design the network as close to reality as possible. And actually, any prediction model will do a good job, I think. That you can compare different network options. I also added something here about 3D predictions, and I think that's in urban areas generally it's an overkill, but in built up in the terrain like Switzerland and Austria, of course, you can use it with lower resolution, like 20 meters, and that also Norway, I think, is using a 3D model, and that's very, very powerful when you use it right. Okay, yes, okay, so what is the summary here? It's a clearly defined target, as I said. If you don't define the target, you will never get there. And the interaction between broadcasters and network providers is very important. You should iterate your plan, nominal detailed plan, a few iterations is advisable. And then also balance the size of the SFN. I haven't talked much about it, but it's the size of the SFN to avoid self-interference is important. And then I think you should plan first. I've seen many examples where they actually bought equipment and just rushed ahead without knowing what they wanted to achieve. So define the requirements. And if you do that, you have some chance of achieving that, yes. Yeah. With that, I say thank you. Sorry for exceeding my 1 minute. Yeah, okay. Thank you.
So, thank you very much for inviting me. I'm very happy to present today. And I would like to give you the point of view of a regulator when we approach this issue of planning. So I'll try to show you something that Mats very well introduced before. So you'll see something of that made real in practice. In 20 minutes, maybe I'm not able to express all the details and nuances of the planning activity. Maybe I'll have to skip some slides, but I'll left those to you to have a reading later. So, first of all, I'd like to point a few things from a spectrum regulation in Italy. In Italy, spectrum regulation is made by two administrations. One is AGCOM, then we are the National Regulatory Authority, and we are independent from the government. And the other is the Ministry of Enterprises and Made in Italy, and that is the government. This division is set by the Italian law when we took in the European code for the electronic communication. So this is not common in other countries, but it's the way we do it in Italy. So by and large, we can say that the AGCOM is in charge of spectrum assignment plans for electronic communications. So we do the actual regulation for spectrum assignment. And additionally, for audiovisual frequencies, including DAB, including TDAB, we do also the planning of the network planning for those frequencies. After that, the ministry is in charge for assigning the rights of use of spectrum. So to say, giving the network rights to the actual operators, while we do plan without knowing which operator will run a given network. What I'll cover today is one aspect of those. One aspect of this arrangement, that is exactly the planning of TDAB broadcasting frequencies. My clicker won't. Okay. Oh. Okay. So you'll see only the red box on the left, the frequency planning for TDAB. After that, we need a plan for assignment the frequencies to the operator. That is done also by AGCOM when needed. And then the ministry will grant the rights of use of spectrum to actual operators. And after that, the operators can run the network. In order to understand also this process, I have to add the fact that in Italy we do have currently DAB, commercial DAB running since if I remember well, 2012 or something like that. We have 3 national operators and a few numbers of local operators, but those are now working on a provisional network planning. And only last 2 years ago, we made a structured national plan for DAB frequencies, and the ministry is currently running the process for giving frequencies to the new operator and implement the new plan. So the new plan, which I will talk to you today, is not yet on the field. There are a number of problems. Maybe if there are some questions, I can deep the troubles. So just I try to go very quickly. We should start from somewhere, and we of course we have to start from the law. And the law says that we have to plan, other than the efficient use of spectrum, we have to give a uniform coverage to all Italian territory. And we have to make a balanced distribution of frequencies between national and local operators. You'll see that in Italy we have a lot of local networks, regional and province networks, but we have to do that by law, because we want to pursue the objective of promoting pluralism. And we have also other constraints, like the need to provide the coverage of at least 70% of the population, and we decided this to be done outdoor, mobile consumption of the service. Okay, let's go. Okay, basically now I want to go into much detail on that. Mats already stressed the need to use a number of standards and that are commonly used by any planner all over the world. And we have also the obligation to publish everything we do. So we have all those standards and other technical criteria are published in our decisions, also in order to make sure that the other bodies involved in the chain are able to do their job. I refer to first to the ministry that should assign the networks to the operators, and also later to the operators for realizing, implementing the network in the field. Just to recap that we use in Italy only the VHF third band, under 74 to 130. It's a standard band, but we could not use all the band because the law in Italy says that in case of need, one channel should be reserved for TV, and we had to do that. So channel 5 is taken away from TDAB and used for multiplex in television planning. I don't see my counter, so maybe you give me one minute when I'm 1 minute. Okay, that's one of the main constraint we have in our job. Where do we get frequency from? We have the need to respect the international coordination agreements. Italy is a long peninsula in the Mediterranean, my friends, Croatian, would say that Italy prevents them to go straight to make vacation to Ibiza. But when we talk of frequencies, we need to protect also the utilizations of a huge number of countries in Europe and in Africa as well. So Italy had to do a number of agreements with bordering radio bordering countries, where we have those agreements. Spectrum is used in a more efficient way between the involved countries. Where we don't have those agreements, we shall use GO6, that is an international agreement, maybe less efficient than what we can do by negotiating, but it is there. So we have a number of agreements. I made the list here. Where we don't have the agreement, so in the Adriatic Ionian part of Italy, we use GO6. That's why we were able to make 2 years ago the plan, even if the agreement with our colleagues on the other side of Adriatic Sea and Ionian Sea, this agreement is still discussing, and we should arrive sooner, hopefully soon, to the end. In that case, of course, we would have the need to modify the current plan, because for us, an international coordination agreement is mandatory. So once those agreement is signed, we have to modify some frequencies allocation in the Adriatic and Ionian Sea area, coordination areas. Italy, as I said, is unlucky because we are in the middle of 10 coordination areas. I don't see okay. So here you see all those coordination area we have, and in each area we have to respect the international agreement. So it is not an easy task. So the frequencies available are those that I mentioned before. After we reserved 4 DAB for TV, our leftover are 9 DAB blocks. By law, we had to provide at least 3 national networks. So we have 6 left for local operators, local networks planning. And with the hypothesis of reuse 2, we can plan at least 3 local networks. So in conclusion, our objective was to plan 3 national multiplexes and 3 local multiplexes in each local service area. I'll show you how those are identified. And of course, if some frequencies is still left, we could plan other networks on a more restricted local service area, like a province. Here you see how an example of mapping the frequencies allocated to Italy by the International Coordination Agreement to service areas. There is only an example. The first row is channel 10, then 11, and then 12, just to have an idea of the complexity of this net framework of frequencies. And here you have an example, just an example, to see how by reuse 2 we could design networks on local areas. The same color is the same frequency, and each area is an Italian region. So going on, planning criteria. Okay, it's a recap of what I said before. We had those are our starting point for planning, and of course we should have differentiated the composability between various local network, local service areas. So as I said, 3 national networks, at least 3 local networks for each area. Here you have some technical criteria and parameters used in planning. I won't go into detail here. Mats also mentioned a lot of those. Here I only would like to stress the fact that we used the minimum reception quality at 95% instead of more qualitative 99. It's an intermediate value between good and acceptable, and in the end we had to strike a balance between the number of networks and the quality. Here you have other technical criteria. For the propagation models, we use both the 1812 and the 1546, depending on the actual case. When there is a C, we use the statistical, and also we had to mandatorily use one of the others when there are when this is mandatory in the coordination agreement with the foreign countries. If the agreement says you should use the 1546, that is mandatory for us. Okay, this is just to show how we proceed to prepare our plan with this constraint. We start from a compatibility matrix between allotments. Then we start an iterative process, starting from a frequency distribution table, the preparation of the point of verification, and then we verify that everything is in place with a software tool. If the solution is not found, we modify the frequency distribution table and iterate the process until we get to a solution. After that, we go to the draft plan. So the first step is the definition of the compatibility matrix. This is between areas. An area is an allotment, the minimum area that are also included in the international agreements. The matrix is allotment by allotment, and we see whether two allotments can be compatible for a given frequency. After that, we know which allotment are compatible or are partially compatible. That means that if we use the same frequencies on these two allotments, some restrictions should be made on the pertinent transmitters. After that, we group a number of allotments to form a local service area. I said that local service areas are regional, because is an administrative requirement for us. And if there are some leftovers, frequency leftovers, we go to province level. So in the end, after we prepare the allotment compatibility, we distribute the frequency we had in place from the international coordination agreements to the allotment. And this is the most complex step. The objective is to planning the highest possible number of networks. After that, we prepare the so-called PDV, point of verification in English. In Italy, we call it PDV, and it's known to all as PDV. We prepare a huge number of PDVs, both in the national territory of Italy and also in the foreign countries. Each operators, at the planning phase, we prepare those PDV based on the reference planning configuration. And we prepared this framework of PDV that should be respected in Italy and abroad. This PDV is in the end is a threshold. It's a threshold to that the user of the frequencies in that allotment should respect in any PDV in Italy and abroad. And to give you an example, the threshold is the value I indicated, almost 40 dB on microvolt per meter. Here you have an example of what does it mean to respect a PDV. For example, there is a local operator A that has a network in central Italy, Lazio, and with channel 12A, and it should respect the thresholds in all PDVs, in all areas where there is a PDV in Italy and abroad. And from the International Coordination Agreement, the operator A knows also the sum of interferences that should be tolerated. After that, we verify the distribution of frequencies with a simulator, and eventually we iterate until we find the solution, the best solution. When everything is okay, we pass to the draft plan, and we are obliged to make that public, and we should run a public consultation. Any operator interested can answer, and we try to, of course, listen to any proposal that comes from the market. But as in any other public consultation we run for any job we do in AGCOM, we are not obliged to accept the modification, the proposal from the market. But we are obliged to motivate why we don't follow the, let's call it, suggestions. In case, of course, there is a good suggestion, we took it on board, and we did that in our last plan in 2022 for some issues. I want to go into details. So in the end, we pass to the final plan. AGCOM is a collective body, so my office prepared everything I described so far, and then there is the board of AGCOM that take the decision under a decision, a formal decision that is then mandatory for the Italian market. Our plan in 2022 provided for 3 national networks with one SFN structure in macro areas, 54 local networks with regional structure, and additionally we had other 36 local networks with a structure usually at province level. So it's a huge number of networks in the end. Here you see exactly the plan. This is the plan. That's the 3 national networks, and this is the mapping of the local, the 90 networks I mentioned. So going to the conclusion, we AGCOM as pushed the DAB market since the beginning. We started with a regulation for DAB in 2009. But we had to wait until 2022 to do the first structure of the plan, because we had to wait for the VHF band be vacated from TV, and that happened after the TV switch over from when the 700 MHz band was used by 5G. So we had the possibility to reshuffle all the TV market. I want to stress 2 points in our activity. We pursued the consortium market model for operators. I said that we have 3 national networks, but one is used by the public service broadcaster, the RAI in Italy. The other 2 are in the provisional plan are assigned to consortia of enterprises, of operators. That's because we wanted to accommodate as much as possible demand for that service. And that's also true for the new coming local networks. Also there we have a consortia type. Then you are wondering why we put all this effort for squeezing all those local networks from our plan. The reason is that we have an overcrowded FM band, and we wanted to provide at least in theoretical transport capacity to accommodate in case almost all the FM radio market. Of course, there are no plans to shut down the FM sector, but we are ready with that to accommodate those transport needs. As I said, the process of translating our plan into reality is in the hands of the ministry. There are some troubles. Actually, there are some lawsuits filed by some national operators, one in particular. I won't name it. But we to wait the conclusion of those, the ministry has to wait the conclusion of that process, juridical process. So I tried to give a flavor of our job. Is different from your job as a broadcaster. We have to plan with a different mindset. We want to make the best use of frequencies, not for the sake of efficient use of spectrum, but also for the need to fulfill Italian problems. This objective of pluralism is very present in Italy, and also we have to plan with the scarcity of resources as always. So thank you for listening to me.
Thank you again, and hello, everybody. Thank you, WorldDAB, for sharing the invitation to this event. So let me connect directly to the title of the seminar, because we are speaking about plan, measure, and control. So in my opinion, these activities need always an interactive approach between the activities, because we need a continuous improvement of our network. So we need to plan, to measure and control during our activities. So my presentation will cover 2 main topics: the importance of the antenna design and a quick overview how we can control the result by the measurement. So first, let me spend just 2 words about our company, ALDENA. We are one of the historical European antenna manufacturers, thanks to 45 experience and hands-on experience. Why the slogan "Antennas in tune with the future"? Because the challenge is develop solution in line with the new effort for quality, efficiency, and performance. So today we are able to provide tailor-made antennas for broadcasting application, radio, television, analog and digital signal, custom antenna for mission-critical application, together with added value services like consultancy, training, and so on. In addition, we introduce in the market a special tool, Electromagnetic Lab, is focusing in antenna design, advanced antenna design, together with coverage and interference calculation, and RF exposure compliance analysis, that in some countries this task is very, very important. So let's move to the digital radio. General point of view, you can see that the planning process is really complex because cover different aspects. A lot of actors are active in the process, not only the broadcaster. We have the regulators, we have the services provider, we have feedback from automotive market, together with other activities like commercial activities, legal activities, and marketing activities. And of course, finally, but not least, the engineering part that is more closest to the audience today. So our goal, the target, is guarantee the best quality of service, limiting the cost of transmission. So we need to maximize the coverage, minimize the interference, and solving, in some case, the electromagnetic impact situation. Of course, we need to coordinate the license. We need to have national coordination and international coordination for license fulfilling. Network planning is part of this complex scenario. Our network can be planned for national coverage, regional coverage, of local coverage. It depends about our license. ABU provide, in my point of view, this reference document, the 3391, that give us a quick overview about the parameter that can be used for DAB network planning. In particular, in the document introduce different scenario, different reception mode that we can use for our network planning, starting from vehicle mounting receiver up to standalone receiver or standalone handheld receiver. And it's very useful because you can understand how many parameters are involved for calculating the minimum signal strength. And of course, this parameter can be adjusted country by country, but general point of view give us a very detailed report about the different reception mode scenario, that this is our target for the coverage. In addition, the document provides also some consideration about the SFN network. Of course, compared to the MFN network, using the SFN, we can use the same multiplex, guarantee the same services in the area, and we need to keep in our mind the number 74. This is the maximum distance between the transmitter that we have to manage. And here below you see some a reference table about what's happened when the signal we receive signal outside the guard interval. So this is a really important reference. So the suggestion, the general suggestion, you normally do coverage calculation, but you need always, during the process of planning, take a look on the interference calculation, self-interference calculation, because in some case, we are able to understand where the area are located. We can try to move or reduce the self-interference. In some cases, it's not possible, delete completely the self-interference, but we have to manage it and move in maybe in some area where there is no people and there is no target area. An example of network rollout. This is a typical example. We are in Italy. We have 3 national operators, Railway, and 2 commercial operators, WorldDAB and DAB Italia. This is the example from WorldDAB. The coverage today is very good. They are using 6 SFN network, as my colleague from AGCOM described before. And they are online with less than 200 sites with different ERP level, because we choose an hybrid configuration between high tower, high power, and low power, low tower, because the Italian landscape is very complex, so it's really complicated. We have flat terrain, we have mountain, we have a lot of neighbors, so it's a very complicated task, but today the result is very good. So we introducing the ERP. The ERP is our reference number for make the right antenna design, the effective radiated power. So is related to the power generated by the transmitter and the antenna gain. So ideal, the antenna gain is a sphere, but we have to customize our pattern to reach the target. So when we speak about gain, we speak about the directivity of our antenna. So the capability to concentrate the energy in one direction, for example. So, and every time we have to analyze our trade-off between the cost of the transmission site and the cost of the antenna or the dimension of the antenna. So on the market, you can find different antenna model, starting from dipole, panel solution, directive antenna like log periodic or Yagi antenna. So you define your base antenna and you start to optimize your horizontal and vertical partner to calculate the final gain of our antenna system. Some example of horizontal radiation pattern. So we can start in an easy way using dipole antenna over there. Otherwise, we can add more elements in our antenna. So we are speaking about Yagi or log periodic. So this means that we are concentrating the energy in one direction. We add more gain. We have more gain. Or we can use a standard configuration composed by panel, 2 direction, 3 direction, and 4 direction. But in some cases, this is not enough because we need to create special diagram to respect, for example, the ERP limitation that the authority provide us. So this is exactly a real case from UK. This is a small scale DAB antenna. It's exactly a real case. How we can customize the diagram. We have to work anytime in this parameter. So we have to select the right antenna, and then we have to modify the mutual distance between the elements. So we can modify the vertical distance, we can modify the offset between the antennas, and we have to work on the electrical parameters. So we can manage different power and different phase for each antenna system, for each single antenna. Some example of spatial configuration. This is a simple way to concentrate the energy in one direction. So to obtain more gain, we are using log periodic antenna in this example. We call it in Italy broadside configuration. So starting from one antenna, we introduce in the same plane 2, 3, and 4 antenna. You see how the shape of the horizontal diagram is narrow. So this means that we have more gain. Otherwise, another typical example that we suggest to limitate the influence of the antenna system in the cross-border coordination. This is very simple, but very powerful. We are using just 2 antennas and just, again, shifting and moving one antenna and phase compensate, we can reduce the signal on the back. This is very powerful when we need to reduce energy in one direction. Let's talk a little bit about the vertical diagram. What's happened when we start to introduce more antenna? You see the result here. So our shape will be narrow. So this means that we introduce more gain when we introduce more antenna. Of course, this is another trade-off because we have to understand the space that we have in the tower to guarantee this type of solution. General point of view, rules for the vertical distance is 0.9 lambda. So this means that in band 3, the vertical distance between the antennas is about 1.4 meters, but it depends about the antenna manufacturer suggestion. And what's happened when we double the number of the antenna? The general rules is anytime we double the number, we increase about 3 dB the total gain. This means that anytime we double the number of the antenna, we can reach the same ERP using half power. So this is an excellent trade-off for the energy consumption. When we add more antennas, of course, we have to go in little deep on the vertical diagram because we need to optimize the vertical diagram because we need to guarantee more service. So in some case, we have to introduce an electrical tilt. In some other case, we have to introduce the null filling. You see the result from here and here. Last but not least, in some countries, there are some restrictions in terms of electromagnetic radiation. So when you use more antenna, you are able to reduce the secondary lobe. This is normally the activities that we have to perform for optimize our vertical diagram. So we optimize the horizontal one, we optimize the vertical pattern. So we are able to rebuild a 3D irradiation solid about our antenna. We can use a detailed terrain, so digital terrain model together with the clutter, together with population data. And now we start to calculate our coverage area or calculating the interference. On the market, you can find a lot of propagation model. We were speaking before about the propagation model. These are the models that are normally used for broadcasting application, not only in Italy. Especially we are speaking about 1546. This is an empirical model. It's normally used for interference analysis. In Italy, we have a good feedback using the 1812. So normally used for coverage planning. And the main difference is a deterministic model. 1546 is based on statistic curve. The 1812 use the specific path for each point in our target area. So this, we normally use this one in Italy. As I said to you before, our landscape is really complicated, but the results are really good. The setup, we start normally with terrain resolution around 100 meters, and then we go up to 20. I agree with Matt, 20 is the right compromise between accuracy and time, because, you know, make propagation analysis also needs time. But what I want to, the message that I want to give you is, remember that you need to use a reliable antenna pattern. So ask to the manufacturer to provide you all the diagram, not only at the mid of the frequency. We need diagram for any channel, and we need also phase information for each antenna, because this is a key point where an antenna optimization and antenna design is necessary. Let's move finally to a real case study. So this is a simple antenna. We are located in the north part of Italy, in Valle d'Aosta. The antenna is simple, as in addition is also isolated by the SFN because a lot of mountain create obstruction. So it's a good case study to compare the design and the results. So the antenna is shared between the public and railway and the commercial, the DAB Italia operator. The design is simple. We use a compact double dipole, and the target area is covering the main road between Courmayeur, La Tuile, Morges, all these small village cities. So the operator choose the double dipole, and the final ERP is about 0.3 kilowatt. So it's this means that transmitter is around 100 watts. So we are in a typical situation for DAB plan. Another key document that I would like to introduce you is another document from ABU, is the technical report 051, and give you a general overview about the measurement. So a lot of different case study are introducing, speaking about how to control the service quality and how to control the network quality. So about the service quality, the easy way to perform the control is the drive test. So we can perform drive test very simple using a roof-mounted antenna with the GPS, the DAB receiver. We using in this case study one of the most famous software is Observa to make the measurement. And sorry, the report suggests you to take in consideration for define the scale of our quality, the bare result. So we can define no service, good or adequate service, and excellent services. So let's go in our case study. So we perform the drive test during the winter time. So we choose always bad weather condition. And you see here the result exported in Google. We don't lose the signal except in the tunnel. So the quality was very good, especially in this area, and was adequate or good also in the other area. So, but the quality and we received the sound, everything, in every place. Let's compare to the simulation. We use 1812, and we discover some difference, especially in that area. Our measurement showed that we cover the area with higher level than we expected. So this is a typical situation where we need to make another type of measurement. Well, we need to deep in details with this kind of performance. So the report suggests us to analyze the network quality. How is it possible? Using ground-based measurement. So we set up a van, we set up a specific antenna, we go up to 10 meters to analyze the signal, and we select, you see our setup here. We're using a omnidirectional antenna, but it's also suggested to use a log periodic antenna pointed on the specific tower. And we select some checkpoint to perform our comparison and measurement. What we discover, that we have a couple of points perfectly in line of sight, so the simulation match the measure that we perform, and especially the point number 2. In the point number 2, there is no line of sight, and the simulation doesn't match the measurement. Why this condition? This is a typical situation when we receive the signal not directly from our tower, but the signal comes in the opposite side. So we have a reflection that came from the mountain. And we discover also the reflection using a log periodic antennas. So in this case, typical case when we have valley or small valley, the reception is better than the prediction. So finally, some conclusion. In our point of view, of course, you need continuous improvement. So you need to have good planning, good measurement. You need to design from the beginning your network, and you need to customize your antenna fulfilling the requirements. So the antenna design is really, really important. Don't be afraid to adapt your planning when you go on air. So make measurement, make survey, and make optimization after you switch on the transmitters. All these information are really useful to tune the specific prediction model that we are using, and is a good know-how for future coverage problem solving. So thank you for your attention.
So the title of the presentation is DAB Plus measurements in complex scenarios, but it's really about our measurement experiences. Shortly on the content, for the introduction, a little bit about OIV, that's our company, about our DAB Plus network and our measurement vehicle. Then a little bit on stationary and mobile measurements and our experiences with that. Checking the radiation pattern of the antenna system with the field measurements, a little bit on portable measurement devices and some other tests that we did, and a short conclusion. So I'm coming from OIV. That's short for Odašiljači i veze, or in English, Transmitters and Communications. We were formally founded in 2002 as a separation from the public broadcaster HRT, but we have existed for many years within the HRT, and we have a long-term experience in broadcasting, 98 years of radio and 68 years of television broadcasting. In the last 20 years, we have broadened the scope of our services apart from broadcasting. So now we are one of the leading service and network operators in the region, in the area of terrestrial and satellite broadcasting, transmission capacity services, multimedia services, and different kind of professional services. And as for the WorldDAB, we are a member from 2018. A little bit on our network. We have started with the DAB Plus with the trial in 2017 with 4 sites, and then extended our network year by year. The commercial or regular operations we started in November 2021 with 10 sites, but soon the network was extended to 27 sites. This is the current situation. So we have around 97% of the population covered with mobile outdoor signal and around 66% with a portable indoor signal. And the highways, we think they are covered around 96%. But that's not, the network is not finished. This year we are planning an extension. We will add 9 new sites, and the main targets are the highways and the state roads. And in addition to that, we are conducting a pilot for a tunnel coverage, 3 tunnels with different approaches, different technologies, different vendors, to gain some experience in that area. So on to the measurements. So I'm talking about the RF measurements for the coverage checking purposes. So the main tool for us is our measurement vehicle. It's a van, you can see it here. It's equipped with motorized telescopic mast, 8 meters, plus antenna support, 2 meters. So we have a classic 10-meter height for the measurements. On the antenna support, there are remotely controlled rotators for the polarization and azimuth adjustments. And we use the log periodic antennas for all bands for the measurements for the FM, band 3, and UHF. And additionally, for the mobile measurements, we are using the rooftop antennas, dipoles for the UHF, DAB, for the DAB and for the FM whip antennas. And on the rooftop, there are also GPS and compass antennas for the system. This is the workplace inside. The main instrument that we are using is a Rohde & Schwarz ETL analyzer. We are doing most of the measurements with that instrument. Then we have a DEVA DAB control receiver and a DEVA mobile FM radio analyzer. They are behind the screen here, you cannot see them. Then the mast and rotator controls, power supply controls, switchover matrix for the signals, and the PC that basically runs everything. It has a software for the mobile measurements on and our network databases. First, about the stationary measurements or the fixed mobile measurements. We are doing those for several reasons. First, because it's a regulatory requirement in Croatia. Then the stationary measurements are good for the SFN control. Our network consists of 6 digital regions, and that means we have 6 SFNs. And we have had examples of bad transmitter time settings that were detected during the measurements and corrected. And in general, the stationary measurements are good for the verification of the network performance in the long term. Because when something is changed within the network, we can compare the results before and after, and we can detect the possible problems. Like I said, for the measurements, we are using the log periodic antenna on 3 to 10 meters height, like described in SEPT recommendation 7402. That's the method of measuring of the field strength at fixed points. On each point, we have to find the right position, so no reflecting objects and no overhead conductors. So no power lines, no telephone lines, no antennas or buildings with metal roofs above. The mast and the antenna is fully automated, software controlled. We have a site database, and the antenna is automatically directed to the transmitter. We can do it manually, but automation works fine. And as for the level, the ETL measures the voltage, but we have the results immediately in the field strength because we have inserted the antenna gain and the attenuations within the system. This is the example from the measurement campaign that we did. That was the regulatory requirement. One of the license obligations was to measure within every settlement with over 1,000 inhabitants on at least 1 point. So this resulted with a little below 500 measurement points statewide. These are the snips from the measurement reports, the table with the results, and the points shown on the map. On each point beside the field strength, we are recording the MER, relation error ratio, and BER before Viterbi, and we are checking the channel impulse response if the SFN is okay. Some examples. These are the screenshots from the ETL analyzer. This is the example where everything is okay, so the signal level is very good, BER, MER is good, and channel impulse response is also perfect. This is the example when the the SFN is not properly set. So we have a significant signal level. I'm trying to find the pointer. Well, never mind. We have a significant signal level outside of the guard interval, so the reception is compromised. The signal level is okay, but the MER and BER are bad because the SFN signals are not aligned. This is the signal, this is the example with the so-called 0 dB echo. So it's the situation when we have two signals with the same or nearly the same level within the guard interval, and it impacts the MER. It's in this case we have to have a signal level a little bit higher than usual for normal reception. When checking the coverage in a certain area, probably more interesting are the mobile measurements. For that purpose, we are using the rooftop antennas and the Rohde & Schwarz BC Drive software. The measurements are presetted and done automatically with GPS position taken for every point. And when finished, the data is then exported to the geographic information software for the representation, like shown on map here. We are using 3 colors. You can see it here: red for the signals below 43, green for the signals between 43 and 66, and blue for the signals above 66 dBs field strength. Those are the levels from the EBU 3391. We are using those both for the coverage prediction and for the measurements. As for the coverage prediction, we are using one of the softwares. And within that software, we are using the ITU 52526 recommendation methods. So somewhat different than what we heard so far. We are doing the prediction on 1.5 meter above ground. Of course, we are using DTM, digital training model, 20 meter resolution, and it's giving us a pretty good results when correlated to measurements. We have typical examples here. The above graph is showing correlation between measurements on fixed points and the prediction. And you can see here that 93% of the measurements are within the 6 dBs from the prediction, and the average error is minus 1.23 dBs. Mobile measurements are below correlation. So in this case, we have better results. 94% of the measurements are within 6 dBs from the prediction, and the average error is 0.22 dBs. One of the purposes for the field measurements can be to check the radiation pattern of the antenna system. That is, if you are not using the helicopter or drone for that. You can try to do it with the field measurements like we did. This is the example from renewal of our VHF band 3 antenna system for the DAB+ on our site Sjeme above Zagreb. You can see it on the photo here. We have done the measurements, both stationary and mobile measurements on the old and the new antenna system, but we couldn't compare the results directly because the old system had a different pattern than the new one. So what we did, we have calculated the coverage using the planned new antenna pattern, and we have compared it to the mobile measurements that were done after the new system was set up. And we have found that in southeast segment, we have a problem. You can see the diagram here, the map, and Those red measurements here are representing the problematic part, and it actually corresponds to the minimum in the diagram, in the pattern. So we found it, and we had a slight intervention within the system after that, and we improved the situation in that segment. So what else? We are regularly checking the channels that we use in our networks for the interferences. The most problematic part is our coastal region because of the propagation of the warm sea. Signals are going all the way across the Adriatic and cause problems to both Italy and Croatia, especially during the summer. So every summer we do a measurement campaign on the same 9 points, and we check the situation. And the FM channels are pretty bad still, but the DAB+ channels are interference-free at the moment, so hopefully it will stay that way. So all of those measurements are done with calibrated equipment. But for quick checkups, we have portable measurement devices like Hexalon from Certal here. And we also use the Observa for the mobile measurements. It's a handy tool because it can be fitted with any vehicle. With that kind of portable equipment, for example, we try to find out how much the buildings are suppressing the DAB+ signal to find out how much is the so-called building penetration loss. So we have done measurements in front of and inside of different buildings, and in around some 50 measurements, we have found the average difference was around 17 dBs. It's a big difference, but it's not a surprise because majority of the buildings are from the reinforced concrete and using metallized glass windows. So final few thoughts. So in our opinion, the network quality is a prerequisite for the promotion and success of digital radio. Quality of service is without a doubt important to clients, both broadcasters and listeners. And reliable radio service is important in crisis. OIV has always been aware of the importance of the measurements and quality control. On the photos here, you can see our measurement vehicle in action. That is sometime during 1970s, so some 50 years ago. And finally, field tests as measurements are important because you never know who is listening. That's it for me. Thank you.
Hello, everyone. So we are a company called Xperi. We designed something called DTS AutoStage. And I want to talk briefly about what DTS AutoStage is. I have a slide. There we go. So I'm going to be very brief. I won't give a long sales thing here. What is AutoStage? We are taking analog or digital, and we're basically adding an IP pipe. So that allows us to add certain things. So a live guide. So we can actually show you a station list in your market and what is playing live on that. So what artist is playing, new show, whatever that may be. Also allows us to do higher resolution images. So that could be, in this case, if you have something like a Mercedes with a 146 centimeter screen in the front, they have a higher resolution they'd like to see. Also, additional information. I'll kind of show you what that is. This is an example. So this is, looks like Queen's Killer Queen. It allows us to see something up here. You gave us the, as a broadcaster, they may give us a artist. They may just give us a song. But what we can do is supplement that with how long that song is. When did that song come out? Lyrics to the song up in the right. And we are the only global lyrics solution in the car right now. Also, you could do something like this where we could show other metadata about Queen. So allows you to give us, the broadcaster gives us information, we can then supplement that. But let's go into the real cool stuff I like. We have about almost 50,000 radio stations globally working with us. We also have about 143,000 different broadcasts that are live. That number in the middle, 2.1 billion hours of enhancing, that's closer to 3.5. That's our prediction for the end of the month. And also, we're working with about 12 OEMs. It says 6.5 million cars. My hope is by Thursday or Friday, that'll be about 6.7 million cars. And I want to kind of show the car companies very briefly to show the global aspect of this. Mercedes, of course, everybody knows. BMW, we just introduced as our newest partner. We have Tesla, which you all know. Hyundai, Nissan, Ford, there's a lot. You can see the logos there. We also have 6 others who will be launching over the next 12 months. So we have, as I said, almost 6.7 million cars globally. This is the past 7 days. So this is showing radio coverage. This could be analog or digital, depending where you are in the world. And we have quite a few, as you can see, about 159 countries and almost 50,000 stations that we're basically getting information from. The interesting part is something called the broadcaster portal, and that's something myself and my team are very proud of. What we do is we allow broadcasters, as these guys were talking about how they plan DAB, we allow them to see how that radiation pattern and where their users are. So in other words, where are they listening to your radio station? So in this case, first things are first, privacy. We take this very seriously and our whole system is built on it. So we are basically built up from the ground up. Privacy was the whole focus of it. So broadcaster data, so in other words, if you're a broadcaster, your data is your data. You have full control of your data. And we also try to protect with the various laws around the world. Every country has different privacy laws, which we follow, and we protect the broadcaster from anything regarding that. The fun part is what we do next. The broadcaster, this is Bauer in the UK, you have full control of your data. So in other words, logos, information, and it affects the car. So in other words, if you put a logo in your broadcaster portal, it goes immediately to the car. So we can see that. If you change your logo, change your genre, change the format, you can see it take place immediately. But we're getting to the more fun stuff in a sense where you control the metadata and you can see that. So you can see when you do something in the portal, you can also see how it affects the car itself. So you can have an effect. And going back to ancient Greece, you have the 5 W's in the H for how. So the question is who listens to you? And in the radio world, we see frequency patterns, we see the radiation patterns, but where are the users themselves? Sometimes it's in a city area, sometimes they're just passing through a mountain or a valley where they may not have any cities there or towns. Also, the concentration of your market, that's also very important. When they're tuning in and out of a song. So that's the important of the when. The how is how they're listening. So we monitor the analog and the digital frequencies. So that allows us to look and see where your listeners are listening to and how. So are they listening on DAB? Where do they fail over to FM or AM in some cases? Also, what is the programming and how is that programming being interpreted by the audience themselves at the car? But the fun stuff is the reach. So you guys saw the radiation patterns that Matt and the others have shown. What we are doing is we are looking at that pattern for a station, and we're telling you how many cars are in that area and how many are listening to your station. That gives you your station reach, your performance, and how you're doing. The next part is your day parts. People have seen day parts for many years now. But the big thing here is there's a gray line, maybe hard to see. That is your baseline. So in other words, in this case, we're looking at you can't see in the slide, but it looks like a Friday. So on a Friday, what is your normal pattern? The more data you get, better your baseline. Your baselines are always based on how much data you have. The question is what happened on this day? They were pretty close, in this case, Nova, Denmark. Pretty close to their normal pattern. At 12 o'clock, there's a little bit of a change. What was that? It could be anything from a news break, voting, elections, those types of things, weather event. You know your market better than anybody else. As a broadcaster, they would know it. Also, if we're looking at here as an audience, we can also show them where they are. So this is one of the first times, other than looking through a diary and trying to compilate that, we're actually showing you where the cars are, the concentration of the vehicles, and who are listening. So in this case, you can look at it on your individual analog or digital sides. So you could look at your DAB multiplex, you could look at your FM towers, and see how they're listening. In this case, the fun part of it is once you have this data, you can actually zoom in on it. So you can actually go and look down on a neighborhood level of where your users are and where they're listening. So we're taking the radiation maps and basically putting the users and the cars in there. So basically think of it as 6.7 million monitors on the road. Where they're listening, what songs they're listening to, those are very important. So for a station, they want to know who's listening to what song and for how long when they tuned away, those types of events. The neat part is what we're doing next. So this is a year ago we introduced this. We continue to iterate based on feedback from broadcasters, from planners, multiplex providers, et cetera. So the first thing we're going to be doing is adding the number of vehicles. And we call this the serviceable attainable market. What that means is in that radiation map that you see, the question is how many cars are there? And you want to know how many cars, what's your sample size? So this allows you to know not only if you have 20% of the market, how many of those vehicles are there. So in other words, how to target maybe better and how to look at those as a whole. Second thing we're doing is allowing you to stitch these together. So looking at your FM or DAB areas, knitting those together, selecting those, then coming up with a map to show not just the radiation aspect of it, where the tower is and where your drivers are listening to your station as they go through. So this allows you to look not just at a local level, but if in this case, as you all know, DAB has national models, they have regional models, they also have the hub and spoke model. Whatever your model is, you can select what you want. It allows you to present that to your multiplex providers or to the station themselves. Also, it allows us to look and show you the percentage of listening. Since we know where the drivers are, we know what tower they're listening off of or what multiplex they're listening to, and then basically tell you the percentage of that. And that becomes important for a lot of providers. They want to know, what's important. And the insights become a little better here. What countries are listening to DAB? You guys probably can think of this as alphabetical. I didn't put it through a number. All these you've seen before, Australia, Germany, France. These are all very popular. But the question is the transition. We all know about Norway. Norway transitioned from digital, away from analog to digital. In the case of, I'm just going to take two countries here just by random. Well, one was semi-random. Spain is random. The question is they're talking about going to full digital. The question is how have they changed? So I just took the top 25 stations for the country. A year ago, they had about 4 DAB stations that were in their top 25. The next year, it's only 5. So the thing is, this is not the time for them to transition purely digital. Now, Switzerland is a little bit different. So Switzerland is really, really good numbers when it comes to DAB. And I think the people who have done all the planning have done an excellent job here. The thing is in the top 25, they mostly focus on cities. And I was talking with Matt about this earlier. Focusing around the cities, a majority of those top stations are DAB. But the question is the other parts of the country. And about 65% of all the listening currently is still done on analog. So even though Switzerland had originally talked about end of 2024, I'm very glad to hear they extended to 2026. There's still a lot of listening on analog, and it will take time, as we all know. A fun example, this is an example to give you on what digital has in this case, is we had a company come to us and they said, we have an FM station and we have 2 multiplexes. And we want to know what our listening is. And I showed you that earlier about how many they're listening into on what type of transmitter or multiplex. In this case, they were thinking about getting rid of the FM. And they said, we don't believe we need it anymore. We believe we have full DAB coverage here. So this is a Venn diagram. You've seen it, so different colors. Most of their listening was on that DAB. That's the pink and the blue that you see here. But as you see, as we cross over, you can see where those colors change. And when those colors are changing, you're seeing that's where they're, the DAB coverage is excellent. But on the right-hand side, you see in the yellow, that is where the FM, that's still, even though it's only 6% of their market, that's a pretty big market for them. So as a broadcaster, they can work with their provider on the multiplex. They all can start their planning and decide what they want to do. And this gives us insights not just as broadcasters, but also in the whole field of DAB. It allows us to see what is best for the customer, what the best coverage is, and we have all of these monitors going down the road at high speeds, allows us to see things that we've never seen before. So the big thing is what we're trying to do here is about big data. We have AI and machine learning models, and those models are basically trying to predict what is best for the customer in the car as the user, but also allows the industry, especially for DAB and DAB+, is what's the best way to do this planning for the broadcaster, but also for the user in the vehicle. So for a broadcaster, how much does this cost? It doesn't cost them anything, it's free. So what we do is we get information from a broadcaster. We basically get their static information. That's their logos, their descriptions, those types of things. And that is used to help us, get a base record for them. The next is we do a streaming URL, and I was sharing this with somebody earlier. There are times when, as we discussed here in planning, you'll find areas where there is that clutter aspect of things, where you start losing signal, where you start going in between, where it may be difficult because maybe of the train or whatever the clutter may be. So what we do is we allow the broadcaster to provide a streaming URL. What that does, it allows the radio to basically fail over to a stream, allow you to keep the user intact. And then once DAB signal is returned, or FM, or whatever the signal may be, it can then flip back over to the actual analog or digital signal themselves. Then they also give us live data. So the live data is basically what's playing, what songs are playing, what show is playing, that type of a thing. What that allows us to do is then take that data through our machine learning models and provide this back to the broadcaster in those descriptions I saw before. Now, those descriptions and of the sessions, of the maps and everything else, those are actually per broadcaster. We don't share it with other broadcasters. We don't share it with marketing groups. We don't do any of that. Broadcaster's data is a broadcaster's data. So that privacy aspect is key to everything we do. So that is our system, and that is it. Thank you.